Appendix 4 Chapter 1 on single particle interference and the concept of the potentiality waves. In this appendix, we will take a look at how the wave-like basis of the reality was discovered and how the concept of the potentiality arose in this context. We will do this by starting out with the general properties of the waves and the particles and with a phenomenon that physicists call single particle interference. On the properties of the particles and the waves. Many of the phenomena studied by the physicists involve phenomena of the everyday life, such as the behavior of waves and particles. They are easy to understand because you already know them very well. Everybody, I am sure, must have some experience with board games, either watching a game or playing a game. Baseball, football, soccer, bowling, or tennis, you name it. The center of attention is always these delightful little things, the ball, which moves about with a certain speed and bounces around. Basically, the property of ordinary balls define very well what physicists mean by a material particle. When you take an ordinary object and divide it into smaller and smaller parts, at some point you arrive at the elementary units of the matter that you cannot divide anymore, right? That is the level of elementary particles. As to ordinary things, they are all made up of atoms. The word atom derives from the Greek word meaning indivisible. Yes, indivisible. As it turns out, atoms aren't really indivisible. They are made up of smaller elementary particles called protons, neutrons, and electrons. Atoms are tiny things. You can think of them as a tiny ball with a diameter of 1/10 billionth of a meter. The word particle derives from the Latin word that simply means a small part. You divide things, you end up with a small parts. The concept of an elementary particle implies that at the bottom of the things, we find units of mass that behave like the objects that are composed of them. So, by definition, elementary particles are compact and localized lumps of matter. They are impenetrable and fill space solid. They bounce off of one another when they collide in space, like pool balls. As with balls, I am sure that you must have had some experience with waves. Sitting on a beach, watching the wave roll in the form of the infinity of the ocean or swimming in them is a wonderful way of enjoying life. Waves are everywhere. The sounds around you, for example, consist of the waves. There are waves in their air that you can't see, but you can hear them when they strike your eyes. The best way to start thinking about the waves and their property is to realize that a wave is not a thing, but a process. Yes. A wave is not a static structure, but a dynamic appearance. Something, a medium in which a wave is propagating, has to move in the characteristic way of the waves, up and down or back and forth, and again to produce a typical motion of a wave. Water waves swing in water, sound wave swinging in air, light wave can swing on their own in a vacuum. Wow. Yeah, because light needs no medium, right? Neither medium nor oxygen or atmosphere, which is medium. Yes. The water molecules in the ocean have to move in the circle to make waves, and they have to do that in a concentrated way. Graphically, we can present the up and downness of the wave by a typical wavy line, as shown in the figure 1. When several up and down movements are repeated, when two, three, or many mountains and valleys follows one another at regular intervals. We speak of a wave train. I am sure you have seen such trains of waves move across the water surface. The top of the mountain of the waves are also called their maxima, while the salts or valleys are called the minima. The height of its maxima or the depth of its minima defines the amplitude of a wave. See the figure 1. Yes. There is a characteristic contrast between the property of our particles and waves that has to do with the fact that one is static while the other is dynamic. Waves are appearances that are extended in space. Particles are localized. A typical property of a wave is a length, called a wavelength. You can define it as the distance between the two maxima and two minima. See figure 1. Another typical property is the number of times that the ups and downs in a wave train repeat each other in a certain time. The frequency tells us how often that happens in a second. Right.